Assalamu alaikum and welcome to this session. Actually, before going inside the induction motor design and all that, I thought of actually having a small review session for induction motor. We have done the Viva and all that sorts in the last two lectures, but the performance has been quite below par. So this session of just like 30-40 minutes, I want to actually talk on the induction motor, the questions which I have posted on the website also, and also on my website and MS Teams also. Without delay further, I will just go through all the questions, and whoever wants to actually do an induction motor revision from your machines course a little bit, I'm going to deal all with that over there. The first question, if I have this one, if you have this file over here, what is an induction motor and how it has a similarity with a transformer? Now, this question has been answered previously also, and many of you will be knowing this one. The similarity between an induction motor and a transformer is very much the reason behind a transformer and induction motor being very same is this, that an induction machine, the rotor winding, which are actually the windings on the rotating shaft over there, they are short circuited. This is the very important thing, they are short circuited. And if I'm talking about a transformer, the secondary windings, which are actually the windings on the secondary side, they are open circuited, of course, certainly, and they are connected to the load. Now in induction machine, if I go back, the rotor is short circuited because the electrical part of the rotor has to be short circuited, because there is going to be a current flowing through the rotor, and that current carrying conductor is then going to be flowing, having a current, and that conductor is going to be inside a magnetic field, which I am talking about, the magnetic field of the air gap. So then it will actually develop a force on it, and that it will actually try to move in a circular path. So induction motor, the output is not electrical in nature, it's mechanical in nature. So this portion over here, that is actually the rotor being short circuited electrically, is actually going to produce that mechanical, and to produce a mechanical force, we already know from elementary classes the simple Fleming's left hand rule, which is actually telling us that you actually want a current carrying conductor placed in a magnetic field. So I hope this is known to this. So in induction motor and transformer, there is a very remarkable similarity between the two. They both have windings. They both have the primary winding. Here in induction machine is called as the stator winding. Here in the transformer we call this one as the primary winding over there. And in transformer we call this one as the stator winding over there. And if we talk about in terms of the axis of the windings in transformers, the axis of the windings, they are in the same, which means that all the three phases of a three-phase transformer, if I'm talking about, they all have the three same axis over there. There is no change in axis. But if I have a three-phase induction machine, then the axis is actually having a 120-degree phase difference. So we will come this to a little bit detail. If you want a little bit more detail, you can consult any book on this one. But the reason of actually having this axis over here, or difference between the two axes of the windings of 120 degree, is because you want actually a magnetic field that is revolving. And transformer, there is no concept of revolving magnetic field. But certainly there is a magnetic field, and that is revolving, and it is certainly revolving with a speed which is already, you know, this formula, that is N20F by P is equal to NF over there. And here there is no speed, so this is actually zero speed over there. In fact, there is no concept of revolving magnetic field inside a transformer. Then very important thing, or very important difference between a transformer and induction machine is this, that here in transformer, the leakage flux, which we talk about, the leakage flux is happening inside the air over here. What is that air? That air that is between the two limbs of a transformer. Some of the winding flux does not go through the iron. It actually flows through the air and complete its path. That is actually called as the leakage flux over there. But if we talk about an induction machine, the leakage flux is that flux which is retaining inside the stator core, if I'm talking about the stator, or little bit flux which is also a portion of the rotor core. Why is that so? The useful flux inside a transformer, if I talk about in terms of useful flux, so a useful flux of a transformer, that is inside the core over there, that is flowing through the three limbs of the transformer core, if I'm talking about a core type transformer. And if I'm talking about an induction machine, the useful flux, it will flow through air gap. So all the flux which is actually going to be converted into the electrical equivalent of it, or maybe it's going to be again interacting with that electrical current of the rotor, and it's going to have mechanical force being produced. So all the flux which is actually going to be converted into either the electrical counterpart or the mechanical counterpart, it's actually going to come through the air gap. So the useful flux is through the air gap. I mean, here the air gap which I'm talking about is actually the air gap between the rotor and the stator. Now a question can be asked over here, we will discuss in the very much detail when we will discuss the air gap when we will be designing an induction machine. But just for now, a larger air gap means that there will be more reluctance. So the flux will have to actually travel a longer path through a larger reluctance one. So this is a very detrimental thing. But on the other hand, if the air gap is very, very small, it is actually mechanically very difficult, so that the stator and the rotor, they are perfectly aligned together. By perfect alignment, I mean that the two magnetic materials, which are actually the stator and the rotor, they have the exact air gap on all 360 degrees of the rotor and the stator. Why is that so? Because maybe there is a faulty bushing, a faulty bearing or something like that, and then there is a slightly little bended towards the stator on one side. So what will happen? There will be centripetal forces or centrifugal forces over there occurring, and it will be having an attraction on one side. So this will be detrimental for the operation of the machine. So a air gap of larger one will have not that much difference over there. Plus a larger air gap is also very good for having a large reluctance for the winding over there. We will talk in this much detail, we will discuss this in much detail, but at present just remember this, that leakage flux is actually the flux inside induction machine that retains inside the stator core. We want the stator core to be producing the flux that should be linking with the rotor or the rotor winding, and we want the rotor core, the flux that is actually being produced over there because of the rotor current, and the rotor current is actually being produced because of the induced EMF. Now one thing very important over here, which is very important difference also, in transformer we always get an induced EMF because of n d phi by dt, and we all know this is actually the Faraday's law of electromagnetic induction. Why d phi by dt is happening? Because there is a change in flux. And why this is happening? Because there is a sinusoidal EMF being applied on the primary winding, and certainly on the secondary winding there is going to be a d phi by dt. And if the number of turns are increased than the other wide side, you are going to have a larger EMF, and then this means it's going to be a step up transformer, and if it is on a lower side, then certainly it's a step down transformer. In induction machine, it's a little bit tricky over here. Why? Because it is certainly d phi by dt, but this d phi by dt is not happening because of the flux changing. This is very important over here. The flux is not changing. Actually, the flux or the magnetic field which is being produced, it is a constant magnetic field. This is very important. The revolving magnetic field has a constant magnitude of B. But since this is revolving, the conductor inside the rotor is going to actually experience a rate of change of flux of it. So when it is revolving, it is going to experience a change in its d phi by dt. So it's going to actually experience a EMF induced inside it, and certainly there is going to be an n number of turns over there, and then it's going to have an EMF induced. Plus one more thing, when the rotor is going to actually start rotating, because certainly at some time will come, the EMF will induce, the current will start to flow because the rotor is short circuited, and you are going to have a EMF induced, and the current is flowing. That current is going to interact with the air gap flux, and the air gap flux is going to have the Fleming's left hand rule, and then the mechanical motion starts. The rotor, that is NR, is going to be the speed of that rotor. That NR will try to reach NS. What is ns? Ns is the revolving magnetic field speed, which I just showed you over here. This is what was ns equal to 120 f by p. So now when that rotor will try to reach that speed over there, but that difference will still remain. Now this difference between ns and nr is very much important, because this ns minus nr is actually called as the relative velocity or the relative speed between over there. Now this difference is more, then this means that you are going to have a more induced EMF. Now let me explain this with another point of view. You have a magnetic field from the stator side, that is the EMF, that is actually the magnetic field over here, and that is having a constant magnetic field. B is constant, the magnetic field density of that is constant, and it is rotating with the speed 120 f by p. If rotor starts rotating with the same speed, that is ns, the both are moving in the same frame of reference. They don't have any difference. The stator winding is saying that the rotor is stationary. The stator magnetic field is saying the rotor is stationary. The rotor is saying the stator is stationary. So what will happen? Because in induced EMF case, if you remember it, the formula from the elementary physics was that E was equal to VBL. Now, what was V? V was the relative velocity between the conductor and the magnetic field. Now, when you did this formula over there, at that time, the V was the velocity given to the conductor at that time, because that conductor was being given a mechanical force from some turbine or some other source, and V was the magnetic field that was being provided by some permanent magnets or maybe an electromagnet, and L was actually the conductor length that was placed inside that magnetic field. Now this time what is happening, the V is still constant, it's not changing, similarly just like the previous case of a permanent magnet or something, but here this V over here is actually proportional to ns minus nr. So the stator and the rotor, the stator magnetic field, this is actually the magnetic field speed, and this is actually the speed of the rotor physically. This is very important, that these two should have a difference. If they don't have any difference, V is 0, then certainly EMF induced is 0. So remember this thing very importantly. In an induction machine, Ns is always going to be greater than Nr. This is very much important, true, and Ns can never be equal to Nr, because if this happens, this means actually that Nr is the same as Ns, actually the speed of the revolving magnetic field. You're not going to have any EMF induced over there. And the last case, which is very important over here, somehow you may argue on this one that can Nr be greater than Ns. Now what this means actually? This means actually that the rotor is moving faster than the stator rotating magnetic field. So what this means actually, that the rotor will feel actually that it is not lagging behind, it is actually going forward. So what will happen over here, this velocity V over here means that this is actually going in the opposite direction. So the EMF induced will also be in the opposite direction, and an EMF induced in the opposite direction means that certainly the current is also induced in the opposite direction. So this means actually, because of the Fleming's left hand rule, the motor has to move in the opposite direction, which is against, because here Nr is moving in the positive direction but at a larger speed. So technically speaking, this option, the third option, is not true, and this is not possible as just like the second option. The only true option is the first one, that is where Ns is greater than Nr. The last option over here we just explored, Ns is less than Nr, is also not true because of the law of conservation of energy, because you are putting some power input inside the stator, it's producing a revolving magnetic field, and because of that revolving magnetic field you have now an induced EMF inside the rotor, and then it starts to move with a speed greater than that of Ns. Not possible, because energy cannot be created nor destroyed. So you are actually now having more energy than whatever you have put inside the stator. So technically speaking, or by the law of conservation of energy, this is not possible. So the only thing possible is this, that Ns is always greater than Nr, and the difference of this is very important, this is Ns minus Nr divided by Ns is called as slip. This is called as slip over here, and if I convert this one into percentage slip, then this function Ns minus Nr divided by Ns multiplied by 100, this is your percentage slip. Now one thing very important, since these two formulas are being discussed, I can relate it over here. When the machine is starting from rest, your Nr is equal to 0. So when Nr is equal to 0, at this time your slip comes out to be equal to 1, or if I am talking in terms of percentage slip, then this is equal to 100%. So when the machine is starting from rest, this is very important, but this condition will not remain for a very long time. As soon as you give supply, everything is okay, the winding is okay, the machine will start to run, and that NR will speed up to some value. So this condition of having a slip equal to 100% or 1 will only be just for a very split second over there. That is when the machine is starting from rest. As soon NR will increase, then as we just talked about, that NS will always be greater than NR. So if I have an NS of supposedly 3000 RPM, so what will happen, this NR at no load will be something near about something 2980 RPM. So you can see over there that NR is almost close to NS, and here the slip, if I talk about, is not more than equal to like maybe like 0.01 to 0.03, maybe something like that. Or if I talk in terms of percentage slip, this is not more than 1% to 3% over there. Now this is at no load. This is very important. This is at no load. Now as the machine goes on and its load is increased, and I go something near about, like supposedly it's a very good well designed machine, the speed somehow goes to 2900 RPM. Now there is now a 100 RPM loss. This means now when the machine is loaded, your slip can go on from 8 to 10% over there, which means that percentage slip can go from 8 to 10% over there. This is a very big drop now. So approximately 8 to 10% speed is lost over there. Or if I am talking in terms of S, this will be something near about 0.08 to 0.10 over here. So the maximum slip that can have a machine or induction machine, if it's not a very poorly designed machine, is something near about 8 to 10% if I'm talking in terms of percentage S, percentage slip. But if I'm talking in terms of S, then it is something 0.08 to 0.10. Now there can be machines in which the S can be just limited to something like 0.04 to 0.06, and these are some very well designed machines which have a very good winding, they have a good material, they don't have much losses over there. So they can be. I have just taken the extreme cases over there, which means that when the machine is loaded, that this difference, no, this is not just true for every machine. Maybe you have a machine of something like a 1500 RPM machine, then certainly NR is something near about 1480 or 1400 or maybe 1350 RPM. So there can be different values for different number of poles over there. So I hope this slip and this one is totally clear over there. Now since slip is being talked over here, I can talk about a little bit about the torque slip curve. I will advise you to actually go to Chapman and have a little bit reading from torque slip curve. For just one, we're actually talking about torque slip curve. If I take the torque on the y-axis and I take my slip on the x-axis, so my torque slip curve is something like this. So what is happening over here, the slip is actually 1 over here and this is 0 over here. So what this means is actually when the machine started from rest, it was having a slip 1. So I can have another axis over here that can be called as speed, and here I am increasing from speed to ns over here. Now technically speaking, you cannot have a machine working at ns. So this means certainly the region in which you are going to have this machine working, if I just zoom it a little bit, the only working region of a machine is something going to be like this one. The green color region is actually the working region of your machine, because from ns to a little bit decrease of maybe like 10%, 4% of that is actually the working region. And over here, as you can see, the maximum torque that it can generate, this is the full load torque that the machine can generate over there. So this is the torque slip curve over there, which has actually a saddle effect over there. Now this torque at the point over here, this is called as the starting torque of that machine. And this torque, which is certainly the maximum torque, as you can see, this torque is called as the pull out torque of your machine, and the slip at this occurs is called as Smax, or the maximum torque slip over there. Now these three torques which I am talking about, this is the torque pull load, T start and T pull out, they are very important, and from the design perspective, whenever a machine is being designed, it has to be considered for these three things. Now certainly if you are designing a machine which certainly going to have a large starting torque, then certainly this means you are actually going towards a wound machine. A wound machine is that machine in which there is a specific winding inside the rotor, and that is certainly connected in Y configuration, so that you can actually attach a variable resistor on the outer side through slip rings, through carbon brushes, and you can attach a Y connected resistor so that you can change the resistance. Because over here, I will just draw the equivalent circuit a little later, but just for now, if I change this torque slip curve somehow to like this over here, so this means if the resistance of my R2 was here, now I have changed that resistance to R2 bar, so certainly R2 bar is greater than R2. So this means actually by changing the rotor resistance, here R2 is actually the rotor resistance, you can change the starting torque. So now you can see the resistance of the starting torque, or the starting torque value has changed now. But what is the negative impact over there? The working region over here has now a very small torque over there. So whenever you want to have a wound machine and you want to start it at a very high torque, you will increase the resistance and then you will take it back to R2, so that now the machine can have a little bit full load torque value just like this one. So this is a wound machine. We will talk about wound machine in detail also whenever we want to have it. Otherwise, if you are having a squirrel cage machine, and that squirrel cage machine has to be designed so that is actually just going to be a ring, and that ring is actually going to be made in some eddy, some laminations. This is very important. Now let's talk about the eddy current losses and all those losses happening inside induction machine. Now since you are inputting the power through the stator side, the stator side has an AC current flowing in the three phases over there. Now those three phases, they are having a AC current flowing through them, so certainly there will be a change in flux in them. So there will be eddy currents inside the stator, so you have to have the laminations on the stator. There will be eddy currents over there, so eddy currents have to be avoided, and for that purpose you will have to use laminations on the stator side. Now as far as the rotor is concerned, now what happens inside the rotor, before we are going into much detail over there, the rotor frequency of the induced EMF is equal to S times Fs, where Fr is actually the rotor induced EMF frequency. Now this SFS is actually telling you, because since S cannot take a value more than like something, even at full load, this will have a value of something like 0.04 to maybe like 0.06, or maybe the maximum is something like 0.10, which is approximately 10% of the total value. Now FF is 50 Hertz. If I'm talking about Pakistan, we have a frequency from the grid of 50 Hertz. So this means that your FR, the maximum value it can attain is actually like something, if percentage slip or S is actually 10% or 0.10, the extreme case I'm talking about. So this can be 10% of like 50 Hertz, and 10% of 50 Hertz means that you are actually eyeing towards something like of value of approximately 5 Hertz is the maximum value. So something like over here, you are not going to have a rotor frequency more than 5 Hertz. Now 5 Hertz is a very small frequency. Yes, certainly there will be eddy current losses, but they will be minimal. So in the rotor, the eddy current losses are not that much. So whenever we are drawing the equivalent circuit of an induction machine, we normally ignore the eddy current losses inside the rotor branch, and we take them as since the rotor frequency is variable. Why it is variable? Because S is changing. So when S is changing because of the load, the FR is changing. So when the FR is changing, the eddy current losses are variable. On the other hand, on the stator side, when the machine is working, you always have a current flowing through it. Yes, certainly when it goes from no load to full load, there will be a little bit change in the current, but overall the rotor frequency is the main parameter which is changing. The stator frequency remains the very same unless and until there is a more rate of change of flux over there. Otherwise the rotor frequency is the variable part. So the rotor are made of laminations because they can be detrimental and the efficiency can drop a lot, but as far as the stator is concerned, the stator is definitely laminated so that you can have the eddy current reduced over there. Now if I'm talking about the equivalent circuit of an induction machine, I am going towards the final full form of the induction machine. So if this is the stator side over here, this is RS. I am using S for the stator side, so this is JXS, and then over here I have the magnetizing branch over here, and then I have this one, and I am ignoring the resistance, the branch over here. So this is my ideal transformer. Sorry about this one, this is not there. And then I have over here inductor, and I have resistance over there. Now since this is the magnetizing branch, I can call it as R0. This is actually JX0. One thing very important over here, there will be no parallel branches over here in between these two ideal transformers over here. Why? Because this is an air gap. If there was a material in between these two windings, and talking the primary and the secondary induction just like a transformer, then we would have these two ones over there. Now on the secondary side, or actually that's the rotor side over there, this will be called as JXS over here, the JXSR over here, that is actually the rotor. And over here on the rotor side, this will be called as RR divided by S over there. Now how this has actually been done over there, this is very important over there. Practically, when this machine was working, let me just talk about a little bit on this one. Practically, the resistance is never variable. This is not possible. What thing is variable is actually the induced EMF. How it is induced EMF is variable? Because the rotor, when it is loaded more, which means more mechanical torque is required from the rotor lags behind. Its speed reduces. So what happens? The relative velocity vector between the stator and the rotor, it reduces, and what happens? More EMF is induced. More EMF means that more current is going to flow over here inside the rotor. More current is only going to be possible when you are going to have the resistance reduced over there. But in practically what is happening, the induced EMF is increasing. So in practically, if I want to make a rotor diagram over here, a rotor diagram is something like this, which has a resistance and it has inductance over there, and this one is the variable nature of the induced EMF, and I can call this one as ER, and this is RR, and this is called as JXR, and this will be variable. Now here in this diagram, there are two variables options. One is ER. Why this is variable? Because the induced EMF is dependent upon the difference between the stator magnetic field and the rotor speed. So certainly this is also variable. And secondly, why JXR is variable? Because if you remember XR, this will be equal to 2 pi FR into LR. Now what is FR? FR is the rotor induced EMF frequency, and we just did it over here, that the rotor induced frequency is equal to S times Fs. So this means this is also variable. Now involving some mathematics over there, I'm not going to go in that proof over here. This has been converted into this form. So now there is only one variable over here. Now this actually makes the life easy whenever you are actually having the calculation being done, that one value is variable. Otherwise this one and this one, they both are constants over there. JXR, in fact this is JXR naught, and that is actually also constant value. So overall, the equivalent circuit of an induction machine, this is a per phase equivalent circuit with the per phase value of the voltage applied over here. And this R0 and JX0, please remember, this R0 and JX0 are actually the air gap values. The flux which will remain inside the air gap is actually dominated by this R0 and JX0 over there. R0 is actually the eddy current losses which are happening inside the whole machine. So that's why they have been lumped together in this area, and they have been shown. They cannot be shown in the series branch because they are not dependent on the load values over there. If the machine is working even at no load, it will still have it, and even if it is working at load, it will still have it. So this R0 is the eddy current losses over there, and JX0 is actually the magnetizing branch current for the air gap, JX0 over here. And this JX0 certainly is a little smaller, in fact a large amount of smaller than the transformer value. Why? Because in transformer it's the material that is actually having the flux. Here this is the air gap which is actually having the flux. So this current over here, which is IM, is very, very large over there as compared to the transformer current over there. Okay, let me go back on the equations over there. I guess I have talked about a lot over here from all the questions over there. I have talked about the revolving field, the types of the revolving field, Over here, if I talk about the type of revolving field, the capacitor introduced inside a single phase transformer, single phase motor is actually there for making the machine work. Otherwise, if the capacitor is not involved, it's a pulsating magnetic field. By pulsating magnetic field, I mean that the magnetic field, sometimes it is going upward, then it is going downward, and out of these two directions there is no other direction. So by attaching a capacitor, what you do, you actually ask the machine to actually have all of these four directions over here. When all of these four directions are there, then this is going to be called as revolving in the clockwise direction. Now because it has moved here, then afterwards from here this direction it has moved here, and then afterwards it has moved here. So this is certainly moving in the clockwise direction. But if you have a machine having something like this is called as a pulsating magnetic field, and this is possible if the capacitor is not working. That is actually the single phase fans that are at your home, they are not working. This is called as a pulsating magnetic field. We want something like this, but our design is mostly there for the three-phase machines, so this types of magnetic field stuff is not going to be our concern of study. But anyway, this is there, so I talked about this one. I have talked the leakage flux difference with the transformer. I have talked about the squirrel cage and the wound machine types. As I have told you that the wound machine is going to have a winding which resistance can be changed after having resistor in Y connection or star connected attached over there. I've talked just now about the capacitor, that is the capacitor is added over there so that the machine can have a revolving magnetic field in one certain direction over there. Now as far as the induction machine losses or efficiency are concerned, the induction machine efficiency is not more than, if I'm talking about something in Pakistan, the normal general trend for three-phase machines, not more than 75 or 80%. But if I talk about a Tesla machine or a Tesla car having those machines over there of 170 horsepower or more than that, they can have achieved an efficiency of something 85 to 90%, but not more than that, because induction machine as a whole has other problems apart from the eddy current losses and the hysteresis losses, which are because of the material. So they are also working over there. So induction machine does not have that big efficiency of just like a transformer, because in transformer you had loss of something efficiency of 95 to 100%. So this still makes the transformer as the best efficient device in electrical engineering. Okay, coming on to the next one, torque slip curve. We just talked about this torque slip curve just now, and in this torque slip curve I told you about the 3 points of torque. One is called as the pull out torque, the T start, or the full load torque over there, which is going to be our design parameters whenever we are talking about a machine design. Then coming on, the emphasis on beam flexicity. Now one thing very important as far as induction machine is concerned, if I go back on over here and if I just supposingly want to make a machine over here, supposingly I have a stator, and that stator is I have drawn the stator over there, and I am just drawing this stator outer in a ring over there, and supposingly I have a rotor also placed over there, and that rotor is something like this. For just now, for example, I am going to have a winding inside the there is this winding over here. Let me just make this winding over here, and this is like A, B, C phase. This is A, this is A dash, this is B, this is B dash, and this is C. All of these winding axes are at 120 degrees. I hope you can understand this one. If you can't do it, please go through some machines course. You will have a better idea on this one. These are the rotor windings over there. Just suppose these are the rotor windings, which are certainly short circuited over there. Now this stator is being supplied three phases A, B and C. So what this means by this over here, if I have, supposingly there is a cross inside this C dash conductor, and because of the flux which is produced over there, there are some flux lines. Some flux lines will retain inside the stator core, and some flux lines will be just completing their path partially through the air gap, and some flux lines will be actually completing their path through the rotor also. So some flux will be actually flowing through the rotor, and then now this makes the induction machine a very difficult machine to design, because you have different regions over here. Now if you can see over there, the region which is inside this air gap magnetic field density, we are going to call it as BAV, and this is the most important one. Why the most important one? Because this magnetic field density inside this air gap is going to be the magnetic field required for the Fleming's left hand rule to occur. So this is going to be called as BAV, and the flux that is retaining inside the stator core, we are going to call it as something like the stator core or BCS over there. This is going to be called as the stator core magnetic field. Sorry. So this is going to be called as, and the flux that certainly is going to have, and there is certainly going to be some cross or dots over there on this side, and the rotor is going to also develop some magnetic field of its own. That is going to be called as BR. Now I've just given you three different values or three different variables of B. Now these all have a very different value. Why is that so? Because you are injecting energy from the stator. So certainly this is easily telling you that the stator core is going to be the maximum value. Then the next value is going to be the air gap, and since this is air gap which has a very high reluctance, this value is something going to be near about like from 0.4 to 0.7 Tesla. And if I'm talking about something a rotor magnetic field, this will be something near about 0.8 or 0.9 Tesla. And if I'm talking about the stator core, this is not going to be more than 1.1 or 1.2 Tesla. At that time we will talk about in general numbers. But the point of actually discussing these three over here is this, that these three have three different ranges over there. The reason, the induction machine, there is an air gap. If this air gap was not there, then certainly we could have talked about, okay, just like a transformer, there is a magnetic field density of the iron core, and it will be same throughout because we want it. But here, since there is a mechanical motion of the rotor has to move. So the magnetic field of the air gap is very much important. Now you may argue on this one that I want something, the air gap magnetic field as the best one. It is the most important one. Why not we just fix it, this BAV equal to something like 1.1 or 1.2 Tesla, because the BH curve of a very good material available in Pakistan or anywhere else is something like about 1.7, 1.8 Tesla. So why not fix that one over here? Now the reason behind over here is this, that because since the magnetic energy has to be put from the stator side, the first thing has to be the stator core. So if you are going to put something in the stator core, a magnetic field density of something 2 or 2 plus, which means that the stator core is going to have a saturation. The BH curve is going to go into saturation. It's going to take a huge amount of current to have that 2 or 2 plus Tesla magnetic field density, and then when it reaches the air gap, then it will be something near about 1.1 or 1.2 Tesla or near about that, and then the rotor is also going to be something near about or a little higher than that value. But the disadvantage would be that the stator core is going to be extraordinary saturated, and I hope everyone has an idea on this one. If I have a BH curve over here and this is my BH curve over here, so up till this point over there, if this is my BH curve over here, this is my H over here, this is my B over there, up till this point the machine is linear. But if I go in something like this value, this means I have a very, very large value of H over here, and H is equal to Ni divided by Lc. This is Ampere's law. I hope you can remember this, or if you don't, please revise this Ampere's law over there. So just a little bit increase in B from B to supposedly Bx value, you require a huge increase in current. Why increase in current? Because Lc is the mean length, N is the number of turns. They are not going to change. The machine is the very same. The mean length of the magnetic field is the same. N is the number of turns. You have not changed it. The only thing that can change is actually I, and I is actually the current inside the winding. So a huge amount of current will be flowing, and this huge amount of current will actually lower the efficiency of the machine, and certainly you are putting a large amount of electrical energy, but the advantage is not that much, so certainly the efficiency will be. So many manufacturers, whenever they design it, they largely remain inside this linear region, or they just take a little bit higher up over here, something like that. We will talk about that aspect also, that why they do this one. So that they do it for the same reason, that so that the air gap has something, a magnetic flux density of near about like something 0.7, 0.8 Tesla. so that the BAV, the average, that's why the value, the variable name of BAV is actually used over here, because this BAV is the average magnetic field. But because by average, because certainly inside the air gap, if you are closer to the rotor, it will be different. If you are closer to the stator, it will be different. So we have to take an average value over there. So this is very important, that your BAV is the average magnetic field inside the air gap over there. Okay, now you have to talk on the harmonics in a machine, the flux in a machine, the voltage neutral point. Now one thing very important, since you have gone through the power electronics course up till now, and you know there is a third harmonic always existing inside our electronic circuits over there, and if our machine is connected in Y configuration over here, just like this, supposedly this is A phase, this is B phase, this is C phase. Now here there is a neutral point existing. Now this neutral point is always going to have a third harmonic. Remember, this is a very important point. If your machine has triplen harmonics, by triplen harmonics I mean I am talking about the third, the sixth. Sixth certainly does not exist because it's an even number. Then I have the ninth, then I have the 12th, then again 12th is not existing, then I have the 15th. So all this triplen harmonics, if I continue this one, certainly their intensity will be smaller as their number increases. So the third, the ninth and the 15th, all of these harmonics, if there is a ground path through the neutral, they will flow. And I hope so you remember this thing, that all the harmonics, triplen harmonics I'm talking about, they induce no magnetic torque inside the machine. Triplen harmonics, they don't induce any mechanical motion inside the machine. Yes, when we are going to talk about, I will talk in much detail about the second harmonic, the fourth harmonic, the sixth harmonic, the eighth and so on. And when I'm talking about the odd ones, which means I'm talking about supposedly the third, the fifth, the seventh, the ninth and the 11th, these are the even harmonics and these are the odd harmonics. Now both of these harmonics, they have a problem inside the induction machine, but as far as the triplen harmonics are concerned, I'm talking about the third, the ninth, the 15th harmonic. These are going to be creating a problem, the heating of the machine, because they don't produce any magnetic energy or the mechanical motion inside the machine, and they are going to flow towards the neutral. But yes, if you break this neutral point, you are going to have no triplen harmonics, no third multiple harmonics are going to be there. The reason very simple, the third harmonic always flow through the neutral of the system. But yes, one thing very important, you may argue on this point, we don't have a neutral, don't connect it. Now if there's a very big machine and you have placed it somewhat maybe on a mounting or somewhere, and you have not connected the neutral towards the ground, the winding itself will have a capacitance with respect to the ground, and that winding will develop EMF between the actual ground on which you are standing and observing that motor and the winding. So there will be an electrostatic charge between those windings or the metallic chases of the body and all that stuff. So things will be complicated over there. So neutral point is important for the machine and for the winding safety over there, because Earth acts as a very big ground. So the neutral point of a machine, as shown over here in Y connected machines, this is very, very important, and for big machine it has to be done. This is very, very important. But yes, if the machine is delta connected, where certainly neutral winding or neutral point does not exist, then certainly there is no need of it. But delta machine windings, they have a problem of actually having metallic, the chases of the body or the metallic part of the body, they are going to develop a current or a charge with respect to the ground, and that can be detrimental over there. Plus the third harmonics inside a delta winding, they flow inside the windings and they heat it up. They are not going to be going towards the neutral point or something like that, but they will be flowing inside the delta winding. So this harmonic stuff is going to be very important in the design of induction machines. So please kindly review this from your power electronics point of view and how this is going to be. Now next thing, very, very important, and this has to be understood very clearly and carefully. What is space oriented and time oriented magnetic field? This is a very important point over there. Now if I start from the time oriented magnetic field, every time we make a sine wave, we always plant it with the x-axis as the time, and we call this one as the Vmax, and certainly this is the V phase applied over there. This is a time varying magnetic field. This is the time varying. Now if I apply this wave on a stator, let me make a stator over here, and if I have this stator over here, and I have this winding over here and this winding over here, certainly I can call this A and A dash. Now what is happening over here? Listen to this very carefully. If the winding current is going inside and this is coming out, which means this is this positive side, the positive cycle over there. This means current is going inside this cross and it's producing magnetic field like this one. Now when this is going at this point, supposedly at this point, this is approximately half of the peak value. So what means that the flux around this conductor, let me make another color over here just for easy elaboration. So when I have this magnetic flux, this flux around the conductor is going to be smaller value. When it will reach the maximum point over here, the flux around this conductor will be larger. Similarly, the flux around this dot conductor, because this is the flux produced around this one. So what is happening over there, any conductor which is going to be placed inside the rotor over here, it is going to experience that the flux is changing with time. This is very important. The flux is changing with time. So this is experiencing a time varying magnetic field, which means that this conductor, if it goes from 0 to 10 millisecond, why? Because this is from a 0 to 20 millisecond time period, so the half certainly is something 10 millisecond. So from going from 0 to 10 millisecond, it will experience that the flux near this rotor conductor, first it increases and then it decreases down. This is a time varying magnetic field. Now let me go on towards another case. Supposingly I have another machine, and inside this machine, instead of just one winding, I have, let me make it, supposingly this is the A phase just for now, and let me use another color for the B phase. I can call it B and B dash, and let me use another color for C and C dash. And if I go back on my, so this is my A dash. Now this 6 slots, still they are concentrated winding. I'm not going to go into definition of concentrated and distributed. I have talked about previously in the last Viva section as well. So, but here these are 6 conductors and 6 slots over there, and in which A, B and C, there will be some having cross and dots over there. Now but what has happened over there? The magnetic field, if it's a 2-pole machine supposedly, what will happen, these 3 conductors, if I just make with another color, let me just make it, these 3 conductors are going to have a common cross or dot, and these 3 conductors are going to have a common cross or dot. Now what will happen because of this? They will have a magnetic field flowing like this, and it will be constant magnetic field. That's why I told you that by 3 phases and their axis of the windings, they are going to have a constant magnetic field, and that constant magnetic field is rotating, and that is rotating with the speed 120 f by p. So larger the frequency, certainly larger the speed of that volume. Now this magnetic field with a constant b, whatever that value may be, maybe by 0.4 Tesla, 0.5 Tesla, whatever, it is rotating, and it is rotating. Supposedly it was at this point A. I just let's not call it A, let's call it X over there, and after some time it goes to this value or this angle Y, and then afterwards it goes to Z, and then afterwards it will complete all those 60 angle stops over there. So a constant magnetic field is going from X position to Y, and then it is going towards Z over there. But at the very same time, since if you can see over here in a zoom up over here, these 3 conductors are more dense, so the magnetic field which is going to be in this area is going to be more flux lines over there as compared to the flux lines in this center region over there. So what is actually happening over there? This magnetic field overall in the rotor is arranged in space. By what I mean by this area, let me use another color over here. This area over here is going to have a maximum flux because more flux lines are here. This range area over here in the center, this will be a little less over there because it's in between the two cross and dots over there, and again this area will be having a large. So now what has happened, the flux lines, they are arranged over here in such a way that it is having larger strength over here, larger strength over here, and smaller strength over here. So what has happened, this is a space oriented magnetic field. By having these three conductors over here, you have a space oriented magnetic field over there, and now when you are going to place a rotor over here, supposedly I am going to place a rotor over there, this rotor will experience an EMF induced inside it because there is going to be a rate of change of flux over there. So if the flux is time varying, we call this one as a time varying magnetic field over there, just like over here. And if it is space oriented, we call this one as a space oriented magnetic field. And for induction machine, we always have, or induction, let me call it like a synchronous generator. If we wanted to make a synchronous generator, we wanted always a space oriented magnetic field. Now let me give an example from the synchronous generator point of view. Those who have gone through that synchronous generator from the machines, and if you still remember it, if you remember your stator side of a synchronous generator, it's just like the same, just like an induction machine. And you have a conductor over here, you have a conductor over here, you have a conductor over here, you have a conductor. So supposedly these are all A phase conductors. So I can call this one as A1, this is A2, A3, A4, A5. Now when you are going to have a rotor placed over there, now the rotor is made in such a way, now see this very carefully, the rotor is something like this, and I am taking a salient pole machine, and the salient pole machine, you can see this air gap is different than this air gap and also this air gap. So this shape of the salient pole, this air gap is going to make more flux lines in this A3 conductor as compared to what is going to happen in these conductors, or these conductors A1, A2, A4 and A5. So the combined effect of A1, A2, A3, A4, A5, you are going to have an induced EMF inside all of these with a space varying magnetic field over there. Okay. Can I try to grasp this concept? Maybe do a little bit Google searches on this one, and if anyone has questions, we'll talk about this in much more detail. But as far as now, this is a very, very important aspect, that what is a space oriented magnetic field and the what one is a time oriented magnetic field over there. Then next thing, this is actually about the slotting over there. Now one thing very, very important, let me just give an example over there, or idea. Whenever there is going to be an induction machine and you are going to have, supposedly on the stator side, the variable used for the slots is going to be SS. S stands for slots over here. Don't confuse your simple SS, it will still remain split, but SS is going to be the number of stator slots over there. So SS is something, supposedly that SS is equal to something 36 over there. For example, the SR is never going to be equal to 36 then. This is very important. You cannot have the same number of rotor slots. You are actually going to have then an interlocking between the stator and the rotor, and you cannot make that rotor move. This is a very important aspect. Secondly, the rotor number of slots has to be something, a very different value from the stator slot, and it will induce some harmonics because of this difference. Now supposedly, if I don't take on towards the 36, supposedly I something go on towards 48, for example. Now this difference of between the rotor and the stator slot, it is 12. Now this 12 is again a multiple of 36. So because of this, there will be third harmonics over there. So slotting, or the number of slot selection, is a very, very important factor. We will discuss in much detail, but the rotor and stator slots are a very, very important factor over here. We will discuss this in much more detail. Don't worry on this one question. Speed versus the leakage flux relationship. We have talked about this one, that the speed we all know is equal to ns is equal to 120 f by p. So the speed is a very, very important factor. And as far as the leakage flux is concerned, leakage flux is always the flux, as I have told you, the flux which retains inside the core. Either it's the stator core or either it's the rotor core over there. Now if the speed is changing, magnetic field speed never changes. Only it changes if the frequency applied is changed. So if somehow you are having a cycloconverter or maybe a high frequency or a low frequency inverter over there, and that you can change the frequency, then you can change the speed over there. And if you are changing the speed over there, this is very important over there, if you are changing the speed over there by changing the frequency, this is very, very important that you keep your voltage by frequency factor constant. This is very important, otherwise the induction machine is going to be having a problem over there of either oversaturation or undersaturation. What I mean by this, if the voltage per phase is supposedly something a value of 230 and your frequency value is 50 Hz. Now this factor that comes out to be having 230 divided by 50 is something 4 point something value. Now if you reduce your frequency, which means supposedly you reduce it to something a value of 40, what happens? Your time period has now increased, because decreasing down the frequency means the time period is increased. Now in that same time period, you are having the same per phase voltage applied, which means now there will be more flux inside the core. Having a reduced frequency also means, because Fs is decreased down, your Xs, that is actually the stator leakage reactance, this will be a smaller value. Secondly, your X naught, which is actually the magnetizing branch, that is because of the air gap over there. Since you are having a larger time period, you will have more current flowing inside over there. And if I go back on your equivalent circuit over there, what will happen? This branch, this one was I naught, this current is IM over there. So this I naught current will increase. And where from this I naught current is coming? This I naught current is coming from the stator supply over there, which is actually the rotor stator supply current over there. So what will happen? The machine will heat up. So even if the machine starts working, no problem, but when it will have a more current, because what has happened? This JXS has reduced, this JX naught has reduced. So what will happen? And certainly R naught will be also changed. Why? Because your frequency has changed, your eddy currents are changed, so R naught is going to change. So this frequency reduction, you have to reduce down the phase voltage also. Then you can say, which by mean I that by is this, that you have to have V by F ratio constant. So in other words, if you increase your frequency, now here in this case you cannot increase your voltage. This is very important. Why? Because increasing the voltage means that you are actually going to go beyond its threshold value. The machine cannot come to that voltage and it will actually have the winding insulation damage. So V by F ratio has to be kept constant. You don't want it to oversaturate. You don't want, yes, it will undersaturate if your frequency is increased. But this is the only way an induction machine can run. Yes, unless and until you have designed a machine in such a way that it can withstand, instead of 230, it can even withstand 300 volt. Then yes, suitably you have designed that machine in that way. Then you can take it. Otherwise, mostly the machines, induction machines, whenever they are designed, they are not designed for more than the rated value of the voltage that they are designed for. We have talked about this concentrated and distributed before. I'm not going to talk about this one. Types of faults in machine. Very, very importantly, all of you have those single phase machines, water pump motors, or even these fans at your homes. Whenever a machine develops a fault, it's actually the stator winding which has the fault developed. By stator winding, I mean, if I go back on this one, the equivalent circuit over there, if you see this equivalent circuit, the rotor side, if it is a cage machine, it has no winding inside it. It's just some steel bars having some aluminium, molted aluminium inside it. So there is no concept of a winding inside this rotor conductor. So the only thing is that this RS resistance, it becomes open circuit, which means that RS becomes an infinite resistance. So the winding cannot take that huge heat that has been generated, or it cannot take that huge amount of current the winding is taking, and that huge current can be because of any reason. Maybe the rotor is not rotating. Why it's not rotating? Maybe the bearing is not working. Maybe the bushing is not working. So what happens? The rotor is not moving. The induced EMF inside the rotor is at its peak. Why? Because the relative velocity vector is at its maximum. The stator is still producing the magnetic field. The stator starts to pump in more current to make that rotor move. The rotor is still not moving because it's jammed. Maybe there is a water blockade, or maybe the pressure is not there. Maybe there is a vacuum over there. The pump is not rotating. Or the very simple cause is this, that the bearing is not functioning. It's jammed. So what will happen? The stator current will exceed so much, the heat will be so much that the winding will open circuit. And this is the 95% major cause. Rarely you will see that the rotor is actually open circuited. Maybe in a wound machine, if you have connected a very large resistance and you are trying to achieve something, this one, that is R2 dash, and then you have tried to make your machine run at something at this point, then at this one, and you are putting it more torque over there, then maybe the rotor windings can actually have that open circuit. But otherwise, normally the major fault inside an induction machine, a three-phase even or a single-phase even, it's always the stator winding. And one thing very important, I forgot to talk in the very start, that induction machine is a singly fed machine. By singly fed, I mean that it is only provided from one side, that is actually the stator side. If I have a synchronous motor, it's actually a doubly fed machine, because there you are actually providing a DC excitation to the rotor windings also and towards the stator windings also over there. So let me go on to the next question now. Core losses. Yes, core losses are a very big factor, and I've talked this in much detail, that there is going to be eddy current losses. There are going to be the hysteresis losses over there. Then the low voltage problems in constant torque motors. Constant torque motors, where are constant torque motors? Constant torque motors are in the refrigerator. Why? In refrigerator there is a gas, freon gas or some other gas, and that has to be moved from the compressor to the condenser or throughout the pipes inside the refrigerator or maybe a deep freezer. So what happens if you are having a low voltage? Since they are constant torque motors, they always have a constant load on them. So if you are going to put low voltage on them, they are going to take more current, and more current means the windings cannot sustain it and they will open circuit their winding. So whenever there is a low voltage, those machines which are at constant torque motors, they are susceptible to failure at low voltage. So that's why whenever the elders are actually asking you, or even as electrical engineers, you are telling them that whenever there is a low voltage, please run off to turn off your fridge and deep freezers at the earliest, so that they don't burn their compressors, because compressor is actually a constant torque motor. Low frequency versus high frequency issues, I guess I discussed this one in the speed versus leakage flux relationship. So over here, as far as the slots or the shape of slots is concerned and the winding size is concerned, I will discuss in much more detail in the design lecture after this one. And insulation voltage is very, very important. As I have told you, normally if a machine is rated for 230 volts, it can sustain up till something near about 260, maybe 300 even. But if that 300 remains for a very long time, you are actually having that insulation burned down. So maybe after some time, if you have opened any fan at your home and you have been working that fan at some UPS, which was actually giving a sine wave, instead of a sine wave it was giving a square wave, you will have machine that will have some black part inside it, and that is because of the LDI by dt effect. Because when you are having a square wave, this is a very important point over here, if you are having a square wave, from whenever the current flows from this value, from the highest value to the negative value over here, this is having a very, very large sharp decrease or increase in current in a very small time. So what happens? We know there is an inductor inside the machine, so whenever there is going to be a large di by dt combined with L, which is actually the inductance, even if that is in nanohenries or microhenries, still there is going to be a voltage spike produced, and because of that voltage spike, now this was the current. Similarly, when this is going to happen, this will be something like this. So you can see when this is happening, there is a huge spike over here. This huge spike is because of that decrease in that current over there in a very small amount of time. So that's why whenever you have a square wave UPS, avoid it, and certainly avoid it for some electromechanical devices such as fans or motors, because they are going to have that over there. That's why whenever you are talking about a very good specialized inverter, we always want it to have a sine wave, because here at every instant it's changing, and when it is reaching at this point, then it goes inside the negative slope region or whatever, and then it is constantly changing. So LDI by dt is effect is very small, in fact non-existent in this, because di by dt is changing at every instant over there. Otherwise, when it is changing from a square waveform, this is actually the current waveform and this is the voltage waveform. So you can see whenever this is happening, a decrease in over there is a huge spike over there at the voltage front, and this spike, when it is incident on the insulation, the machine gets damaged over there. Next thing, third harmonic in Y and D connected machines. I think I have talked this one in much detail just now, that if there is a Y connected machine and you don't have not connected the neutral point over there, then certainly the third harmonic is going to be non-existent over there, and if it is not connected, the third harmonic is not going to be there. Next thing, synchronous machine rotor design. I guess I just talked about this one also just now over there when we talked about this synchronous generator. This was a salient pole rotor, and this was going towards moving in stator certainly, and the stator was going to have that induced EMF. This A1, A2, A3, A4, A5 are the 4 conductors or the 4 slots in which conductors are there, and they are going to have develop an EMF inside them, and this was a space oriented magnetic field over there, because this distance is different, this distance is different, this distance is different over there. So that's why you can see this is actually a square waveform. Here at its smallest distance, it's the maximum peak over there. Number of poles in synchronous machine, we will talk this in much detail. I'm not going to discuss this one over there. Now just a little bit over there, because since you are engineers, and I hope so you have the habit of actually observing something in your outer vicinity, single phase fan blade angles. Now these fan blades are not more than 11 to 13 degrees. If you make them more than 13 degrees, you are actually putting more pressure on the air over there, and it will be actually having more airflow, but the power consumption is going to be very much enormous. Now I don't know how many of you, since the universities are closed at present, the recent change in the department which has been done just now in electrical department UET Lahore, is this, in fact in all of the UET now, they have changed some fans in all of the department. In, I guess in the ground floor everything has been changed. The fans have been replaced by a 60-watt fan, and I still have not have the hands-on idea why they have done this, but what I have been told, they have been done so that the consumption is small. But I guess what I have been told by the staff over there or the electricians of electrical department, that the fans, their blade angle is small, and when their blade angle is small, certainly this means their airflow is small. That's why they are only having a 60-watt fan. Otherwise, practically, if I don't want to take actually the name of the company over here, because that goes in the other range of tops, but over here, a 100-watt fan, if it is adequately designed, it should be given a very limited value of the power consumption can be reduced, and you should make effort not on the blade angle, because a 100-watt fan compared with a 60-watt fan, and if they have the same copper winding, same something over there, it's actually the material inside the motor over there, or the winding, if it is 99% copper or whatnot, that is actually the point where you actually have to make it over there. Secondly, very important over there, the dimmer which is used over there on these fans, they are actually making the shape of the sine wave non-symmetric. By non-symmetric I mean, because we want a sine wave over there, but whenever that dimmer is actually being working over there, what we try to make it, we only allow this portion of the wave to work, and we want this portion of the wave to work. Now what has happened over there, if I make a current waveform of this one, I don't know if you remember your power electronics, the current waveform is something going to be like this and like this. This is a discontinuous current, and this discontinuous current is not going to produce a uniform torque. So the dimmers are also a big problem over there of having a discontinuity in the current waveform. Now a better advantage of having actually is this, that instead of using dimmers, you use some resistances over there. By resistances I mean that if you want to change the shape from supposedly from this value, you have a resistance inside it and you change the value over here like this. But the problem over here is that in the previous past, like 15-20 years back, there were these resistance regulators over there in which there were resistances added in series to over there, but the problem was that it was a wastage of power, because those power resistances were actually dissipating that power inside them instead of those fans. But you could actually now you could make those fans even at a very low RPM. Nowadays with those dimmers, with these fans which are installed everywhere now at your homes or in UET, you cannot have the fan working at very low, because what you are making it, you are actually trying to make it like supposedly you want to make something a fan, and you are actually just having this one running in this shaded region and this shaded region. Now what is happening, these are just two spikes over there. These two spikes are of no advantage to the machine, and it is just going to have a small current like this and a small current like this. Now these two currents are so small that the fan will either not move, or it will, even if it moves, you can even count the fan blade sitting underneath it. So technically this is a very discontinuous form of waveform given to the windings. The windings are also being damaged over there. The fan is also not running at our required speed. So this is a very detrimental thing. So dimmers, now there are some circuits over there which have very good relationship as far as dimmers are concerned over there, but they are very expensive, and the problem of actually making them inside a very small space of that dimmer, that's actually one thing. So we will talk about this in much detail if we go on towards the single phase machines over there. And I guess I have talked about this effect of square wave inverter just back now. I talked about this square wave inverter on the winding. If I want to talk about this one, this is the same discussion. This one I just talked that whenever there is a square wave inverter, then the current falls down from a very large value, positive value, to a negative value. There is a huge spike in voltage over there. That is actually the voltage spike, the LDI by dt, and that is detrimental for the winding. Capacitor design value. Capacitors normally are something from 2.2 microfarad to 3.3 microfarad, and normally the manufacturers of these fans, normally if I'm talking about single phase capacitors at present or single phase fans, these design values are required, whatever that value, but the capacitor which they install, they are not of that much good quality. So normally whenever a fan starts to decrease, a new fan starts to decrease its speed, you can be sure on this value that you have to change the capacitor, and you have to attach a very good capacitor inside it. But one thing very important, if you increase the power, if you increase the capacitor value, supposedly it was like something a 2.7 microfarad, and you take it to 3 microfarad in the next change, what will happen? 3 microfarad has a very small XC. Now XC, because you are increasing microfarad, XC is equal to 1 over 2 pi f. So what happens? XC is smaller, the power will, the current will increase, the power will increase. Yes, the fan will start to move with a very high speed or something like that, but there will be an expense on your pocket because the fan is going to take a large amount of current. But yes, if you are more fond of having more power or more speed from your fans, there are two things you can do. One, adjust or check for the blade angles, which I just told you here, that those blade angles are actually a detrimental thing, and somehow if you have put something on those blades and those blades are not according to the tilt angle required, they are not producing that power or airflow over there. Or certainly the next thing is the capacitor, that you have to change that capacitor if that capacitor is not according to its required value. You can go to up to something like 3.3 microfarad. I am talking about this, the largest size of these fans, 56 inches fan I am talking about. Now coming on to the cooling in big machines, hydrogen or nitrogen cooled machines. Now these machines are those big machines. I am talking about something 1 kilovolt or 11 kilovolt machines. These are very big machines, and inside their air gaps there is not just air, there is hydrogen or nitrogen cooled machines, and they have to be cooled down because of the immense electrostatic charges available over there, which can actually produce corona discharges also over there. The hydrogen and nitrogen actually have that insulation strength over there so that they can actually cool down these machines over there. When we are designing an 11 kV machine mostly, then we will talk about this one in much detail, but otherwise just for now, whenever a machine is being designed at 400 volts, then certainly I am talking about something which has just air inside those air gaps. One of you maybe argue on this one that if we take a vacuum inside that air gap, it will be good for the machine, but vacuum, to produce that vacuum, it's very difficult, and you have to make that machine sealed. And since the machine is rotating and it is producing that bushings and all that bearing stuff is there over there, so it's difficult to actually have a vacuum produced over there. But yes, certainly vacuum will be efficient over there because there will be no friction losses over there with the air when the rotor is rotating. Then the effect of the machine materials in machine size over there. Yes, certainly the rotor is very much important over there because the rotor cannot take a speed more than 30 centimeters per second. This is the tangential velocity over there which the rotor material can take. When we will discuss it, we will talk about in much detail that the rotor material, and certainly there is going to be a winding inside it if I am talking about a wound machine, or the material over there, because if you exceed beyond this speed over there, that is actually 30 centimeters per second, you are actually going to go at a very high speed. So this means that you have to use some very good materials over there, otherwise those materials can actually have a very large centrifugal force over there that can actually go on over there. Now, maximum stalling torque concept in electric vehicles. Before I go on towards answering this one and the last question, which is actually the electric vehicles as a new future, one thing very important as far as the manufacturers are concerned, if you are talking about the Tesla motors in America, which are actually the new boom in the last decade, they are actually using an induction machine. They are in fact the only ones which are using the induction machines in the electric car industry. If you are talking about the BMW, the famous one, and their famous design of i3 car, which is a totally electric car, they have a brushless DC machine inside it. That's a 3-phase brushless DC machine, and it has an efficiency more than 90%. Induction machines, very simple to control, but efficiency wise just on the little lower side. But maybe as the course progresses, I will show you some designs of the Tesla motors also, in which they have made a very small machine and that can give 170 horsepower or more than that from it, and that's the size of the machine which we normally use in Pakistan for something 2 horsepower or 3 horsepower. So you can see from the design or the size differences that the machine's material is so much important in this concept over there. Now then, if I go on towards the very new big champion in electric cars, then there is a Nissan, and the model which I am talking about is Nissan Leaf. They actually use a synchronous motor inside their vehicles. It's a very good motor. It has a constant speed, so you need some frequency changing over there. Its efficiency is also on the higher side, not as high as BLDC, but the synchronous motor has the biggest advantage that its speed does not reduce. You can only reduce its speed, which means when you are going to start your machine from rest, which means you are actually going to give a variate frequency over there. So this means you are actually going to have a cycloconverter or maybe a variable frequency drive, which I am going to talk about VFD in a Nissan Leaf car over there. And if I'm talking about something, a Toyota, and since Toyota does not have still a fully electric vehicle up till now, I don't know actually. In fact, if anyone has an idea, please do text me about that. I am talking about the Prius car. This is a hybrid vehicle. I'm not talking about the hybrid vehicles, but Prius is a very good famous Toyota vehicle, and the latest edition, they are also using the BLDC motor. And normally whoever owns a Toyota Prius car, you don't have the information that inside the speed range of 0 to 60 kilometers per hour, the electric engine is actually kicking in, and afterwards the petrol engine is still working over there, but it takes over at something a range of like 58 or 60 kilometers per hour. So normally whoever has a Prius car and you are driving in a city, it's better you drive it below 60 so that you don't consume your petrol, and by regenerative braking you are actually again going to charge your batteries again and all that stuff. And it's a very fantastic car. In fact, if I'm talking about some manufacturers who have actually mastered their art of hybrid vehicles. Toyota is actually the one who is actually at the best of this one. Now, since electric vehicles are being talked about and machines are going to be the one thing which are going to be at the back of this one, there are only two things which limitize the electric vehicles. First one, the battery technology, that which type of battery is being used over there, and secondly, the machine over there or the motor used over there. Now, we want efficient machines, more than 90% efficient machines, so that the battery has to be small, the range that can be covered is very small. Now, if I'm talking about the Tesla car over there, since induction machine is our interest in this course and we are designing an induction machine, so if I'm talking about something, a torque slip curve of an induction machine, this is the same torque slip curve I have talked in the previous one. This is the maximum torque that the machine can achieve over there. Now, in a Tesla car, if you are running, you are at stop over there, you are at rest, and you want to run it at a very high starting torque. You have just put your accelerator on the pedal and you just make it something like this. You have achieved a very high starting torque, and then when you achieve something a speed over here like this, you have gone to like something 0 to 100 kilometers per hour in a very short span of time. You can bring your rotor resistance back to from R2 to R2. But yes, Tesla does not do it. Tesla does not do this one in its Model S or Model X. Maybe in their new 2 version model, that is the Roadster model, maybe they are doing this one. Those who are interested in this one, we can have an extra session on this one, on this Tesla Roadster, because they have claimed over here that they can achieve this 0 to 100 kilometers per hour in just 1.9 seconds. This is huge as compared to even the fastest car in the world, Bugatti Veyron or Lamborghini or Aventador or any other car. They have the maximum petrol engine, they have like something 2.2 or 2.1 seconds, and a Tesla Roadster, if it can do this one in 0 to 100 kilometers, this means 0 to I guess 60 miles per hour, I guess, yes, certainly, which actually equivalents to 0 to 100 kilometers per hour and 1.9 seconds. Now, the point actually I wanted to induce over here is that if your machine is still working at this red color waveform and your working region was something this one over there, if you are requiring more torque from the machine, okay, which means you are accelerating, you want your foot on the pedal, so that now you want more speed. So what this means, actually, you are actually asking more torque over there. So this means you are asking it for more torque and you are going towards that more torque. But yes, certainly you are going to get that torque from the induction machine. But yes, your induction motor has to be designed in such a way that it can go beyond this point over there. Because as I told you, in general, induction machines which are used in the industry, they are not designed for more than from a slip of this. Since this is slip 1 over there, the slip is 0 over there. This region over here which I am talking about is not more than like 0 to 10% over there. But if you have designed it something for maybe electric car, then certainly your slip will be something near about 30% or 40% or the maximum point of slip over there. But yes, if anyone is interested inside this R2 to R2 dash, which means there is going to be a rotor resistance change, and certainly this has not to be done by a variable rheostat, because again this will be a friction point over there with the rotor. It will be detrimental for the efficiency of the machine and the mechanical aspect over there, erosion and all that stuff at that high speed. So certainly electric cars are the new generation, and these electric car generation on the next 10 years to follow on, and in fact now up till now, they are going to change how machines are designed, the materials by which they are designed, they are going to change over there, and this will be a bigger advancement, and maybe you are going to go towards some maybe 95% plus machines over there. One new name in this category is the switch reluctance motor. Kindly Google it out. It's a very simple machine, switch reluctance motor, very cheap as compared to any of these machines over there. Why cheap? Because BLDC over here and here, they are using permanent magnets, so ceramic material, and inside this machine 50 to 70% of the cost of the machine is those ceramic materials over there, which have a life of approximately 10 to 15 years, and that is still comparable with the life of a car normally. And an induction machine, there is no magnets over there, but the control of induction machine is a little complex as far as it's concerned. So switch reluctance machine works on the variable reluctance between a stator and the rotor. We will discuss this, and maybe if anyone is interested, I can have a separate 15-20 minutes lecture on this one. But as far as switch reluctance machine is concerned, it's a very cheap alternative, and some Chinese manufacturers are working on this one as well. It has some problems. It has some problems of low speed, torque being very discontinuous. It can work very good at high speeds, but not very good at low speeds. So there are some problems over there with this machine. But as far as the cost is concerned, because nowadays in the nowadays industry, the cost of any machine, the cost of the lithium-ion battery, which is actually the most important battery at present, or the most one used nowadays, this is the most important. These two concepts, or these two things inside an electric car, are the most important one. The first one, the battery being, and second one is the electric motor over there. I hope this is all from my side, and I hope I have discussed a lot for the induction machine over there, and I have discussed in much detail that how an induction machine is going to behave, and what is the equivalent circuit, how it behaves, how the slip changes, what are its differences with the transformer. And I hope everyone can learn a lot, and you can have actually revise a lot from your induction machine from this lecture. Thank you.